All right, as we are looking through number sense material here, we want to look at and classify a bunch of numbers. But to get an idea of how numbers work, we walk through and we say odd plus odd will give you an even, and here's a few examples. This is something that's completely provable, but we won't do it here. Even plus an even will give you an even, also provable, but we won't do it here. Odd plus an even will always give you an odd. 5 plus 4 gives you a 9. But here, fraction plus a fraction does not always give you a fraction. Sometimes it gives you an integer. So for example, 1 half plus 1 half equals 1, or 1 half plus 3/4 is 5/4. And other people have created their own there. So let's go ahead and start classifying numbers. Whole numbers. These are the most familiar numbers you have. Kind of like whole numbers go like this: 0, 1, 2, 3, etc. So they're all positive except for 0. 0 is neither positive nor negative. And it's evenly spaced. We go up by 1 every single time. So these are called whole numbers. In my diagram, whole numbers are going to be the innermost one right here. And I'm going to use the hashtag symbol there to mean numbers.
What's that? Oh, wait,
Numbers, yes. So 1, 2, 3, but also includes the 0.
Well, why do they like 6?
All right, so next up came integers. So integers would be all the whole numbers above that we just did plus the opposites. So when we are talking about classifying real numbers, I am thinking about a number line, okay? And usually we put 0 somewhere about here. 1, 2, 3. So that would be my whole numbers. These are my whole numbers. But then, if I go to the opposite side of 0, like -1, -2, -3, those are my integers also. So both together are my integers. So let me just write that out. Would be ... -3, -2, -1, 0, 1, 2, 3, ... Meaning goes on forever in two directions, and it's countable. I'm counting up, and I'm counting backwards into the negatives. If we were to look on the number line, notice that there's some gaps, though. I'm hopping from a 0 bloop, 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 to a 1, and I'm missing out a bunch of numbers that potentially are there. Because I could put a dot right there, but can I put a dot there? Can I put a dot there? I certainly can. So what kinds of numbers are going to fill the gap inside of there? Well, good. Some people came up with this idea of fractions. So I like to remember rational numbers as fractional numbers because it's halfway, it's 1/4, that kind of stuff. So fractional numbers, or better, rational numbers are the integers plus the fractions between. These are all fractionable, which means anytime you have a decimal that you can write as a fraction, then it is. So notice this, 0.5, but Swenson, that's not a fraction. Well, I can write it as a fraction, so therefore it's rational. What about 6? 6 isn't a fraction. Oh, but as we said earlier, it's fractionable. So I can write it with an integer on top, integer on bottom. Okay? There are some numbers, though, that I can't write as a fraction like this. So let's fill up a little bit down here. The whole numbers are the most inside. Then we get the integers right here. So the integers are the 0, 1, 2, 3, plus all those negatives. So -3, -2, -1. On top of that, we can have the rational numbers, the fractional. You can turn them into fractions. So 1/2 is a rational number. -43/7, that's a rational number. But so is decimals that repeat or decimals that end. So 0.3 repeating. That's a rational number because it can be converted to 1/3. So those are my rational numbers. The last one, if we have rational, we could also have irrational. And ir means not rational. So the best way to describe this is in terms of decimal. So decimal with no pattern, so there's no repeating of things, and no end. So it's an infinite number that goes on forever, and there aren't any patterns. We call that the irrational numbers. So I'll write that one over here in its own category, in its own box, because rational numbers and irrational numbers are separated. So for example, pi. You might know pi is approximately 3.141592654, etc. But it goes on forever. It goes on forever and it never ends. No patterns at all. So I've got my irrational numbers there. And then the rational numbers are on the left. And all together, we call them my real numbers. And some people might be, oh, Swinton, if they're real numbers, does that mean there's fake numbers? And the answer is, yes, there are. They're called imaginary numbers.
Right.
Any number that I can put a dot on. So for example, I can put a dot right here for 1/2. That is a real number. I can put a dot right here for the square root of 5. The square root of 5 lives there between the 2 and the 3. I can put pi down as well. Pi lives out somewhere over here. Pi is somewhere about there. So any number that I can graph on this line is called a real number. Later on in your Algebra 2 class, you're going to realize, and you don't have to draw this, that there's actually an entirely new set of numbers that spawn off the real number line, and they're called the imaginary number line. That's why I dashed it right there to make you think of ghosts.
What if you have no...
All right, so let's classify these. I'll walk through 2 of them, and then I want you to finish the rest up. What about negative 23? What is the best name that I could give it? The best name that I could give it, right? So this one has to be an integer right here. Over here. This one's positive, but because of the decimal that does end, it has a different... All right, so this indeed is a rational number. All right. Irrational, whole, and rational for those last ones there. All right, on the next page, we're going to refresh ourselves with something called divisibility rules. Please turn to your neighbor. Don't write anything, just talk. What do you remember about dividing things? Go. The rule is if it's an even number, okay? Even number. Or if you have forgotten what that means, you could simply say it ends in 0, 2, 4, 6, or an 8. If the last digit is any of these, then we have a divisibility works. So for example, 566. Because that's a 6, that's even, this works. Okay. 5 is also a fairly straightforward one. This one is ends with a 5 or a 0. That's it. Which actually, while we're here, 10 is almost the same. As long as the last digit, and I'll say ends with a 0, or the last digit is a 0. And by the way, when we're talking divisibility, I want to clarify, we're only talking about integers. 15 divides every number on the planet, but sometimes they're fractions and sometimes they're not. Okay? We're talking about always integers. We're always getting no decimals and no fractions. All right, so for example over here, 35. 35 is divisible because of the 5. Over here, 1010 because of the 0 there. So it turns out 3 and 9 are almost the same. So let's go ahead and write out 3. If the sum of the digits is a multiple of 3. Well, it turns out that's the same down below for 9. except the sum of the digits have to be a multiple of 9. So if I did for 3, I said 3,690. That works. Why? Because 3 plus 6 plus 9 is 18, and 18 is a multiple of 3. It turns out that number I just wrote also works for 9 because 18 is divisible by 9 as well. So this works because of the 18 can be divided by 9 very well. All right, so as we saw in number 4, if the last 2 digits form a number divisible by 4, then the whole number is divisible by 4. 8 is the same, but it's the last 3 digits, if they form a number divisible by 8. So if I were to see this one right here, 10,224, all I have to do is take the 224 and see if that's divisible by 8. So in this case, offhand, I don't know that, so I'm just going to do some division there. And I see I can get 2 in there with a remainder of 6, bring down the 4, and then that's an 8, and that's a check. So because the last 3 digits form a number divisible by 8, so is 10,224. And the last one is number 6. How do we show 6? Well, because 6 is equal to 3 times 2, it's actually those two combined. It's the rule for 3 and 2. In other words, so the rules for 3 and 2. So it has to be an even number whose digits are divisible by 3. An even number whose digits are divisible by 3, or when the sum of the digits are divisible by 3. The 3690 is even, so that's a check, ends in a 0. And because 3 plus 6 plus 9 is 18, and that's divisible by 3, that's a check. So I just have to check the 2 rules there. Check that it's even, and check that it's divisible by 3. And there we go. So I'll walk through the first row with you. So test to see if the numbers on the left, these guys, are divisible by the numbers on the top. If so, we're just going to place a check. Notice that 789 is not divisible by 2 because it's not even. So let's check 3. 7 plus 8 plus 9, that's 15 plus 9, so that's 24. So that's a check, divisible by 3. All right. Clearly, because it's not even, 789 is not even, so it can't be divisible by 4. So 89 is not even, so I can't, it doesn't work for 4. 9 is neither 0 nor 5, so it doesn't work for 5. Let's see, why doesn't 6 work? Oh, because 2 and 3 both don't work. 3 does, but not 2, so it can't be 6 either. 8, it's not even, so I can't, so it won't work. And let's check 9. Checking 9. Well, again, as we saw earlier, 7 plus 8 plus 9 was 24, but 24 is not divisible by 9. So in the end, only 3 works on this one. In the end, only 3 works. The last thing we're going to cover in this topic, just so that we refresh ourselves, is we're going to look at properties of real numbers. And as we said about real numbers are any number that fits on the number line. We can do fractions, decimals, whole numbers, negatives, etc. So we're going to look at a few properties. We're going to identify what they look like in addition, what it looks like with multiplication, and then also show you a common mistake. So that's what the last column is for. It does not work for. So we'll put a common mistake there. Okay, the first one here. The first property is called the closure property. Before we write other things, we need to make some basic assumptions. So above the table there, I'm going to say that A, B, C, I might add more later in a second, are real numbers. So we start with a real number and see what we get. Again, it can be a fraction, it can be a decimal, can be radicals, etc. All right, but the closure property for addition simply says that if you take an A, a real number, and you add it to another real number, it's a real number. A plus B is a real number. Just like we looked at earlier when we said even plus even, that's even. So that means even is closed under addition. You always get even numbers if you add evens together. Same applies when you multiply any two real numbers. A times B is real. Won't go too crazy into this, but it doesn't work. For example, if I were to take the square root of numbers, so for example, the square root of 4 is 2, and you're like, oh, 4 is a real number, and when I take the square root, I get a real number. But it turns out if I were to take the square root of a negative number, that takes me into another world, not real. In Algebra 2, you'll look at that more, that actually we define what that is, and it takes us off the number line to a different number line. But we can't take the square root of something, of a negative number, in the real and stay on the real number line. We move somewhere else, like an alternate dimension, a multiple universe situation. Next one. You might remember this one. It's the more common of them. It has a special spelling, so beware. It's not commutative, it's commutative. The commutative property of addition says this. If you have A plus B, you can also say B plus A. Back and forth. I can move those back and forth. As an example, 3 plus 4 is equal to 7. If I were to switch those around to say 4 plus 3, dun, 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 I get 7. Hashtag holy cracky knacky knoccation. All right, turns out I can say A times B, and that's the same as saying B times A. If you need an example, 3 por 4 is the same as 4 times 3. I get 12 no matter which way I do it. Now, closure property, we showed, doesn't always work for certain operations. In this case, I did the square root. Well, up here, it turns out that the commutative property doesn't always work. What if I subtract? Is it true that A minus B is the same as B minus A? Well, let's just try something. Let me try 3 and 4. 4 minus 3, does it equal 3 minus 4? And let's see. This gives me a 1. This gives me a negative 1. So I can say there is no commutative property of subtraction. In fact, it doesn't work for division. Another one. It's called the associative property. Let me spell it right. Associative property. And the associative property under addition says this. If I have A plus B plus C and A plus B plus C, I have to make a choice. I have to add something first. Do I add the A and the B first? Do I add the B and the C first? Do I add the A and the C first? And the associative property says it actually doesn't matter how you add them together. So either I add these two first, A and B, or I add the B and the C first. And in the end, you're going to get the same answer under addition. Just to throw out some numbers, to give an example, if I had 3 plus 4 plus 5, but I did the first two first, and then I had 3 plus 4 plus 5, and I did the last two first, notice that we're going to get the same result. The first one gives me 7 plus 5, and the other one gives me 3 plus 9, and yet I still get 12. So instead of writing plus, write times. Notice that if I just say ABC, it's implied multiplication. So A times B times C is this. And if I put the group around the first pair, as opposed to A times B times C, like so. I can move the parentheses effectively around, which means my order is slightly changing there. So, for example, 3 times 4 times 5, if I do the 3 times 4 first, or do 3 times 4 times 5, with the latter two being combined first. This first one would give me 12 times 5. The second one would give me 3 times 20, and they both give me 60. Works. Don't, simply because you see parentheses doesn't mean it has to be the associative property. So let's take a gander at this. What if I said A plus B plus C, and then I did this? Is that the associative property? Why or why not? So just to reflect, notice the A comes first here, and now the A comes last. So effectively what I've done is switch the two right here. So this is actually the commutative property. So don't simply say, oh, I see parentheses, it must be the associative property. That's a common mistake. Parentheses did not mean associative. But the converse is true. Associative does mean parentheses. So you have to have parentheses with the associative property. All right. We've got two I's to deal with. The first one is going to be called the identity property. Identity property. Identity is a fancy way of saying, what's the number that doesn't make any changes? What's the number that doesn't make any changes? Under addition, there is a number. If I add this number, I get no changes. Anyone want to take a stab? What number do I add to 6 to keep it 6? Go ahead. 0. So we call 0 the identity. You probably don't need much example to that, but 0 plus 6 is still 6. The value doesn't change by adding 0. And some of you say, but Swenson, that's kind of a silly thing. You're like, well, yeah, it is silly in the sense of it doesn't do much, but it's a very important property. And it's an important assumption. We're stating our assumptions. Over here, multiplication. Is there a number that I can multiply by A so that I still get A? Good. I get a 1. There we go. So 6 times 1 stays 6. So 1 would be called the multiplicative identity. The identity you can multiply. Where this doesn't work, and actually what I'm going to do is pretty much just, some people confuse these two. Just because you see a 0 doesn't mean you have the identity property. So for example, something like this. If I have 3 plus a negative 3, if I get 0, that doesn't mean I have the identity property. So we'll get to that in a second. But the biggest mistake is people confuse these two that I've noticed. The next one is called the inverse property. This is important because every time we add 6 to both sides, the point of doing the adding 6 to both sides is to get rid of probably the negative 6. So the inverse property says, of addition, says that if I have a number, turns out there's an opposite. There is a number I can add to it to get to 0. So anything that I can do, I can undo in addition. By way of an example here, we don't need to get overly crazy, but what number do I add to 6 to get rid of it? A negative 6. In other words, another way to say this is that opposites add to 0. Opposites add to 0. Or let me say sum to 0. Opposites sum to 0.
Wait, do I get a grade if I do?
For multiplication, what do I have to do? Well, what number do I multiply by A to get to 1? Well, the answer is called 1 over A, which is also known as the reciprocal. Okay? The reciprocal. Reciprocals, and that's how you spell reciprocals, multiply to 1. And like I said previously, mostly these two are confused among themselves. Just because you see a 0 or a 1 doesn't mean it is inverse. It might be the other. All right, and the last one. You are most familiar with this one because distributive property, it's something that's been drilled into you for the last 6 years of your life probably. The distributive property. It can work for addition or subtraction, but we'll just write it as an addition situation. So it looks like this. If I have A times B plus C, effectively what we're saying is I can distribute the A into both. So we get A times B plus A times C. If I place a 3 here and a 4 plus 5 inside, it doesn't matter. If I do 3 times 4 plus 3 times 5, in other words, distribute the 3 out, or I multiply the inside first to be 4 plus 5. If I do the 4 plus 5, I get 9. And if I distribute out, I get 12 plus 15. In the end here, I get 27 and 27. So it works no matter which way we do it. An important thing to remember is not that I can send in a product. What you're going to find out is that it's just as important to be able to pull out a product. So this here is called factoring.